Well, thank you so much for having me, and thanks everybody for getting to the end of our day here. We're almost there. So I am with the Illinois State Water Survey right now, and I just finished my master's degree in December. And so I'm going to talk to you about the work I was doing for my thesis today on the multimedia fate and intake fractions of PFAS precursors and terminal degradation products. So what I am doing here is creating a model to look at how multimedia transport influences PFAS. And the model that I am basing my work on is called USETOX. USETOX is a European scientific consensus model created by the Society of Environmental Toxicology and Chemistry in the United Nations Environmental Program. And the way it works is by defining various environmental compartments and then mathematically describing the movement of chemicals between those compartments based on physicochemical properties. And it currently contains over 3,000 chemicals, but none of those are PFAS chemicals. So in 2020, this bottom paper, Hannah Holmquist investigated the possibility of using USETOX to describe PFAS fate and transport. And I took her work and decided to run with it a little bit. So I used the same critical input parameters that she was investigating to create this model. The carbon octanol partitioning coefficient and the bioconcentration factor in fish, I wasn't really able to find sufficient data for in the literature. So I decided to perform an extrapolation and come up with my own estimations for those. So I did a multilinear regression using the experimentally available data for each parameter. And then these physicochemical predictions from OPERA as other predictions. So there isn't any structural basis here. This is not a QSAR. It's just a purely predictive model. So this is an example of how I selected sources and also how that extrapolation turned out. So when I came up with all of those input parameters and made a database of physicochemical PFAS properties, I prioritized newer data over older data and experimental data over estimated data. And this is a good example of how I did that. So I compared different estimation sources against experimental data, which is on the y-axis. So here I'm comparing my new regression for the bioconcentration factor in fish to estimations from the EPA's test in OPERA sources. And my new regression is the one I ended up using. It has a root mean square error of 0.33, which was the smallest out of these, and it best fits the 1-1 line. And this is the method that I used for all of the other parameters that I needed to fill in. So at the end of the day, those different critical input parameters I listed at the beginning, I ended up with all of those for these 49 different PFAS. And so I used that database and stuck it into the USETOX model. And the really cool thing about that is that we can not only do the multimedia transport, but we can get something called an intake fraction. So essentially what I'm modeling is, say I have an emission of PFAS. Here are 5 compartments. Let's pick one that I'm emitting to for this scenario, and then account for the movement in between those compartments. And then I can start looking at human exposure and the different pathways by which humans are exposed. I can calculate how much PFAS they're exposed to per PFAS emitted and sum that up to get an intake fraction, which accounts and turns into kilograms of intake per kilogram emitted. And so then you get a population exposure average. So here's some results on what that means. So this is a scenario for emitting to freshwater. I individually emitted all of those 49 PFAS that I had data on into the freshwater scenario. And another cool thing about having these different routes of exposure is that you can see kind of what the driving source is. So the purple diamonds on this graph represent the log intake fraction. And the different colors are the percentage of that intake fraction that is coming from the different exposure sources. So the range of intake fraction here is about 5 orders of magnitude. And I think that just is a good visual of how much variation there is right now and the different ways that we're exposed to different PFAS. And here for freshwater emission, you'll see a lot of gray bars and blue bars, these dark blue bars, which means that exposure primarily is coming from a population that's ingesting fish and drinking water, which isn't surprising for an emission of freshwater. But these other things represent some above ground produce and dairy and below ground produce, and that is representing the multimedia transport that's happening. These are currently ranked by intake fraction from least or from greatest to least, but we could reorganize these, say, to compare between groups, which is the next step that I'd like to do. So here's the same sort of graph, but this time we're representing an initial emission to agricultural soil. So the majority of exposure is now coming from above ground produce and below ground produce. And then we also have still exposure from fish and a little bit from drinking water. So that's some of that multimedia transport, which is runoff that we would probably expect. But the thing that I thought was really interesting about this was comparing it to these graphs for emissions to rural air and urban air, because the exposure patterns are very similar. And if you zoom in onto this emission to urban air graph, this light blue that I've poorly outlined is representing the fraction of the intake fraction that is coming from inhalation. And the take home point on this slide for me is that, say we're emitting to air and we want to monitor that. If we're only sampling air, then we are only capturing this much of the exposure and we're missing the rest of the picture. So multimedia transport is a very significant contributor to population exposure to PFAS. So I also wanted to look at terminal degradation products, because we can talk about emitting one chemical at a time, but we know that there's multiple things going on here. So with precursors, the way that I included that in their degradation is by defining a fate factor, which is the residence time of the chemical in a compartment, and the removal rate, which is the degradation and movement of the chemical. So how fast is it leaving that compartment? And then you can run a scenario where you emit a precursor, and then using the fate factor and removal rate, you can calculate how much of that precursor is transported to a different compartment and is available to be further biotransformed or degraded into different terminal degradation products. So I gathered a bunch of yield data and came up with molar yield rules based on existing experiments and estimations and based on chain length trends. And so I ended up with enough data to assign molar yields for all of my compartments to these different FTOHs and FTSAs. So essentially what we're doing now is once I've calculated, say I emitted to air, I can calculate how much of 10.2 FTOH is now present in soil. And then I can say that based on my molar yield rules, I'm populating that soil with these 3 different terminal degradation products, which I can then treat as brand new emissions to soil and calculate their respective intake fractions as a result of multimedia transport. So what that gives me, I can look at their exposure pathways too, as kind of a cumulative exposure profile. On the left here, the X or the Y axis is the intake fraction, and then the X axis is the different chemicals. So for an emission to rural air, I have exposure coming from air, but then I also have exposure coming from transport of PFAS of 10.2 FTOH to agricultural soil and then being transformed into PFDA. And this is on the order of grams intake per kilogram precursor emitted. So for agricultural soil, for example, this is suggesting that for each kilogram of 10.2 FTOH that I emit to ag soil, I'm going to get 16 grams of population intake of PFDA. And then this is the same setup, but for 8.2 FTSA. So we're an order of magnitude lower on the intake fraction for these FTSAs, but we have a more diverse exposure profile in terms of how the precursor is moving through the compartments and where transformation is taking place. And something about this is I think this can help to inform sampling efforts, because if we know that maybe our 8.2 FTSA emitted to rural air is more likely to be transforming still within the air, then maybe I won't spend as much time looking somewhere else. And then this, I wanted to emphasize the variability of exposure that's a result of that precursor degradation. So on the bottom are the 7 precursors that I had yield data for, and the X is here. And then these are agricultural soil and rural air emissions. And then the y-axis is kind of like this cumulative intake. So the top bar on each of these columns is the exposure to the precursor itself. And then everything else is a terminal degradation product. So the more colors you see, the more different PFAS that our population is being exposed to as the result of a single emission. And I think that's important as we're looking at setting limits and looking at public health outcomes and toxicity factors. So the conclusions I'd like to really make with this are that multimedia fate and transport significantly contributes to population exposure, and the atmospheric deposition matters. And you think about that air graph in the agricultural soil graphs that were so similar, that's because that deposition is occurring. And that population intake fractions are occurring on the order of grams per kilogram. And I think this work is useful in terms of informing sampling and toxicity experiments. If we can help identify which analytes and media to prioritize, then we can save a little bit of time and money and hopefully inform some regulatory decisions. In the future, this work could be combined also with toxicity data to come up with better population risk estimates and damage exposure. So that is what I have for you today. I'm happy to take any questions.
Great, thank you so much. Do we have any questions at this point? Not seeing anything in the Q&A, but we'll give folks a second to think about it and add a question. Oops. I have a question while we wait too. I guess, I mean, I'm an aquatic ecologist, so I always think about, you know, these contaminants in water, but I also feel like in the media and sort of in the court of public opinion, PFAS in air does not get the attention that PFAS in water gets, even though they're, I would argue that they're, you know, the threat is fairly equivalent.
Yeah.
Right. And do you, I mean, and this isn't necessarily, I don't necessarily expect you to have a great answer to this, but I'm just curious as to what your thoughts are on that and why you think that might be.
I think that it's easier to see the exposure when it's a cup of water, or when you're thinking about, like, people think of water as a really important resource. And even in the Midwest, where like we take it a lot for granted, it's a more common resource. We don't think about air as much unless you're a public health air scientist or something, and then you think about it all the time. And so I think that not seeing it and not thinking about how deposition occurs is part of that. And I also think we just don't know that much about it. There's not that many multimedia studies out there, and I don't know, it's a big world, and there's a lot of PFAS work going on, and there's a lot of things we don't understand.
Yeah. And it's, you know, fairly, even though it's not a new chemical, the sort of urgency to discover and remediate is fairly new.
The urgency, and then if you think about like the precursors, well, if I'm concerned about emitting to rural air, like we are still trying to set limits in most states.
Yeah.
And so I'm more concerned with figuring out how much PFOA is in my water and how much PFOA I should be sampling for in my air. And by the time we've got that all sorted out enough to start looking at these precursors, I think we have to start thinking about this now. Otherwise, we're going to get there and realize that we're just creating more of the same original degradation products.
Yeah, that makes sense.
We did have someone who was interested, if you were able to publish this research, they're interested in more about your biopartitioning methods.
Yeah, so I am working on a manuscript now and hoping to have that out soon.
You.
And then you can always send me a message if you have a specific question on methods and stuff.
Great.